So I'm going to quickly review last week's material, just so that you guys can try to remember. I know it was a little bit difficult. So we covered, please mute your microphones. Thank you. There's a way to turn them off before you get on, so please try to do that. So the normal distribution is what we went over last week. So as I had talked about, the normal distribution is used because everything, when it's regularized, or we call it normalized, or converted into a normal distribution, everything, no matter if it's percentages or sales dollars, is going to fit with the same units. So that's the idea and then we use that for a lot of statistical tests. For the ones that we're going to learn coming up, you have to have a normal distribution or you can't run the test. You have to run something different. So that's why this is important. It also helps us, as we saw last week, with finding statistical significance. And this is very important. This is going to be in class a lot today. So I'm going to try to use my mouse instead of pointing, but because that was confusing on the video. So this big pink part, no matter what your standard deviation or what your mean is, the pink part is going to hold about 68% of your data if you round. So this big pink part here. Whereas the purple parts and the pink part together will hold about 95% of the distribution. And then if you go out into the green, then it's holding a 99% of your data. So the way you know where you are on the curve, the exact middle will be the mean in all cases. And then if you go over here, this is the mean plus 1 standard deviation. This is the mean plus 2 standard deviations, and the mean plus 3 standard deviations. And it goes the opposite direction if you go the other side. So this would be minus a standard deviation, and so on and so forth. This is going to be really important for today's class because we're going to talk about p-values, which are the basis of a lot of statistical tests that you go over. So one thing that I try to do is say, why should you care about this? Where does this fit in? So we talked about the central limit theorem in our first class. So if you take a large enough amount of samples, even if it doesn't have a normal distribution, when you take 20,000 samples of it or 1,000 samples of it, it will then follow that normal distribution. So if you resample the same population. So even if it's very skewed, if you resample, it's going to look normal. So that's kind of the rule of large numbers in statistics. The bigger your sample size, the better you can make inferences or make conclusions about the data and the relationships that you're seeing. So just to recap, the standard error is the standard deviation over the square root of the sample size. This is used to calculate confidence intervals and p-values as well. So as we went over last week, we covered the standard deviation in our first class. The standard error is basically the standard deviation, but normalized or converted to take into account your sample size as well. So this is what it means in words, and I do want to show you these symbols along with the words because a lot of statistics books won't even say the words. They'll just use the symbols instead. And then you got to get used to that idea and before we go into something like machine learning, because then it shows linear algebra instead of something this simple. So try to get used to seeing symbols instead of words if possible and learn what they mean. So the top one is the standard deviation, and is always your sample size. So we also went over z-scores. So z-score is the definition of it, is the number of standard deviations out that you are. So if you're here, the z-score is going to be -2. So you basically convert your data to a z-score, and then you use that again for confidence intervals and statistical p-values. So that's where that one fits in. I'm going over this quickly because I did go over it in detail last week. So this is just, I'm not gonna go over this again, but this is how you would calculate a z-score. The value you're looking at minus the mean. I already covered that. So now to get into the new meat of it. So confidence intervals are used in the vast majority of statistical tests you will use. Machine learning tends to be one of the few exceptions. You can calculate confidence intervals even with those, and they are very important. So you'll hear statisticians talking about statistical significance. So basically, if something fits in a 95% confidence interval, that means it's statistically significant. So if it's outside of that 95% confidence interval, we're gonna get more into what those are in a second. But what does this mean? Why do we use these? So the confidence interval gives us an idea of how much error is in your data. The wider it is, the more error or noise your data has. And it also gives you a way to talk about the level of certainty in your data. So that level of certainty, say you have a 95%, it's significant at 95%, and we'll learn more about this in a second, we would be more sure that our conclusion is correct versus an 80% confidence interval. And that'll make sense in a minute. But as I said, it shows your error around whatever value that you have predicted. So that random error is going to show in the length of your confidence interval. No matter, we've talked about samples and populations. Samples, you're taking a subset of the population, so there's always going to be error involved in doing that. The bigger the sample size, the smaller the error, but that is where that comes in. So this is going to start to make sense why I went over z-scores and why I went over standard errors, and why, because in the context of how I presented it, there was very little way to explain this, and I told you guys to wait and see, and that you would see why. So I'm glad you stuck with me. So you can calculate a confidence interval. So you have a value that is outputted from, say, from a t-test or a chi-square. Those are statistical tests. We're going to cover the first one next week. But to get the confidence interval for that individual value that comes out of a statistical test, you add and subtract the z-score times the standard error. So this will make sense when you see it in context, but this z-score is going to correspond to whatever confidence interval you want to test. Okay, so this is where it should all start to make sense to some degree, and I'll go back to the other slide once I cover this, and then we can go over questions if you don't understand. So as I said, depending on the situation, we'll use anywhere. I actually did use an 80% confidence interval this past week, up to a 95%. 95% is usually what is used in journal articles. Even in industry, they like to have a 95% for the most part. So you would have to choose based on how much error you are willing to have in your estimates. So we were doing in my current job a project that no one has ever done before. Is there a problem?
No, I just can't see you.
Okay, somebody's having feedback. Do you know where that's coming from?
I think it's bad.
Oh, okay. I thought that was feedback from a microphone. Okay, yeah. Sorry about that. So we would, if we were willing to tolerate more error, we would have a smaller, we would use, say, an 85% confidence interval or a 90% confidence interval. If we say we're working with a drug, trying to see if, say, a cancer drug was effective, more effective than another cancer drug that's already on the market, which a lot of statistics is used to do that, we would want a higher confidence interval, because if it doesn't work, if we were wrong, then people are gonna actually lose their lives or go through debilitating illness. Versus if you're looking at sales values at a grocery store, that's gonna be less important. It's still important, but there's more room for error when nobody's going to pass away because you are incorrect. So going back to the standard, to the normal curve. 1.96 is the cutoff for significance for a 95% significance level. So if you want to have a 95% confidence intervals, your cutoff is here. The reason for that, and this is hopefully make all of this put together, and I'm going to go back and explain it again once we have more context. So if we are 1.96 standard deviations out, that means 2.5% of our data is over here, and 2.5% of our data is over here. So we would call something statistically significant. Say we were testing, we're actually going to go over an example later. It's something that they do in the industry, particularly Facebook. I had an interview with them, and this was in my interview. So they'll compare two websites. You'll randomly get selected into seeing one website versus the other, and there's a few tweets in there, and then they'll look how many people click through that website. Say you wanted to see if two websites, one was more effective in creating clicks than the other one. Say they are significantly different. The new improved website is getting more clicks. So your test statistic, or the value that comes out of your statistical test, it will, if it's significant, it will be out here. So the middle will correspond to the mean of the other website. So if the mean of one website is here, and the mean of another website is over here, then that's statistically significant. So we'll go over one-tailed test versus two-tailed test, but for now, think of it in this way. So if we're testing for whether it's different, this would be significantly worse. The website would be performing significantly worse if it was out here, and if it's in here, it's performing significantly better. So that hopefully kind of ties everything together. I'm going to go back to this. So 1.96, that's a very important number. So now this will make more sense. So we have our value that's being tested. So that would come out of a statistical test. And then 1.96 would be here. So that's what I mean by z-score corresponding to a chosen confidence interval. So we know we want 95% confidence interval, that's always 1.96. So we would take that times our standard error. The reason we do that is because, as I said, each sample is going to have a certain amount of error involved with that, so we have to account for it. So then we'll have a range. So real life example of how I use this. So we are looking in particular at, so it would be forecasting sales numbers, for instance. So we take all of our data, historical data, from Whole Foods, look at their sales across stores, and we actually forecast what we think ahead of time what the sales will be in each one of those stores. They use that for using labor. They are planning out for labor. They use that for knowing how much to have on the shelves, and then other things we'll look at what those different values are and how much each individual item sells. But we forecast overall sales by store. So when we forecast, this would be our forecast level here. So if we forecasted, say, there's going to be $3 million in sales at X store, that value would be put here. And if we wanted to have, and we would want to give to stakeholders a level or an interval of error. So if you're, say, we plan for 3 million, well, we're going to have, it's never going to be right at 3 million. So they can look at the bottom and the top of our range and say, okay, it's probably going to be within this range. So they can plan for, okay, we need to have something, say, at the top of the interval. We need to have enough labor on staff to fit that top level and that bottom level. So that's kind of how you would see it in practice. So I'm going to go over a little bit more detail, but are there questions about that now that it's kind of come around? Does that make sense? It's very abstract and it'll make more sense once we do statistical tests, but any questions? Okay. So we already talked about this. So how do you identify what your z-score is? So that's a good question. So let's say I want a 95% confidence interval. So as I said here, 2.5% of our data is going to be down here, and 2.5% of our data is going to be up here. So that's where this number comes from. So if we're going to put something in R, and it's very simple, so you would want to put something in R by, you would want to look at one side at a time. Say you wanted okay.
Oh, sorry.
Okay.
I'll mute it. Sorry.
Okay, thank you. So we would want to look at that 2.5% if we are on one side of our normal distribution. So we would want to test what z-score refers to here. That's the value we would put it in. So Q norm is just the function that does this. If you put 2.5% or a proportion is 0.25 in, it will tell you what the z-score is. So that's where the 9.1.96 number comes from. It will output from there. Say you don't have R. I am actually going to show, and this is how I actually learned it from the start. I think we got some chat. Check, just make sure it's not somebody here. Can't hear. All right, great. So I'm going to go into our value z-score table. So I apologize for the advertisements. They're very obnoxious on this website in particular. So say we wanted to look at that 2.5 number. So we would find somewhere on this table, we would look and we would say, okay, where is 0.025? So we would find that the closest number to that, and then this is why the table isn't ideal. So we would find that 0.025 value. So we would find it in this table. So here's the closest one, 0.25. So if you go up to that, you would then see that it corresponds to 2.06. Now we go back to that 2.5, and you'll see it corresponds to negative 1.9 here. So that's where you can look if you have a z-score table. It'll be in any stats book you ever see. They'll always have this table in there. So this part relates to the decimal point. So think of 1.96 to the 100th decimal. And here you're seeing values to the 1.9, what you would find there. And if you look at the intersection of those two, it's 0.025. So that's another way to understand it. When they teach you this in high school, they make you do it on the table. So I thought it was worth, if you're a visual person, to see it more like that. And you can always look how it ranges on either side and have an idea of how, as you change it, what will change. So. Okay, so I'm going to go out and show, this is actually the only R code we are going over today. I actually have worksheets, believe it or not, for the second part when we're going to go over hypothesis testing. But this, I will go through, and the code is, I will show just for the people who've never been here before. My computer is very slow because of the internet, and it's using a lot of processing power to record. So I would go to kelseyhuntberry.com. So you'll see that right there. or right here. You would go to data science classes, scroll all the way to the bottom, and you would click this statistics in our PowerPoint's code and data, and that's where your code, the code that I'm going to show right now, lives. So I had this in last week's R code, but we didn't get to it, so it's the same that was in last week's as well. So for the people that are new, I'm not going over the programming side of this class. That's in another class. You're welcome to take it. It's going to be a webinar format. We're going to repeat it a bunch of times, but I'm going to show you what they are. I always say in the comments above what I'm doing. So I would recommend going through those comments and trying to understand what the concepts are versus what the actual code does. So this is just pulling in the data. So we worked last week with this, so opioid south. So all of this, it will be the prescribing rates for opioids and the overdose rates in the southern states of the country. So that's already clean for you. So the first thing I wanted to show, and I'm actually going to view and zoom in one more. So these are the values that we're going to be working with. So you'll see here that the median is 97 for the prescribing rate. So that's 97 bottles of pills per 100 individuals. Again, so, and then you're seeing that the mean is 99 in southern states in particular. So we are seeing that range here, and I want to show you that, and I'll come back to it in a second, so that you can then understand better what the confidence interval means. So we are using that opioid south data. This is just finding the mean prescribing rate. So you'll see that here. The standard deviation is 23.6. So we're going to need that in order to do the, I'm going to just recap on these four first. So in opioid south, we are looking at, say we wanted to know where on the normal distribution 105 prescribing rate sits. That's what this is doing here. So it's taking, okay, 105 on our scale of prescribing rates, where is it? In order to do that, we take 105 minus the mean over the standard deviation, and that's the z-score. We went over that last week. So this is 0.25 standard deviations away from 105. So that's where that comes from. Okay, so one of the first things you want to do before you do anything is to check for missing values in your data, because that determines a lot of how you would code things, whether you need to remove the missing data or just account for it in your code. So in this case, when we're looking at the overdose rates, there's 20 missing counties, or I believe, yeah, so it would be the counties in this particular. Reason for that is some counties are really small, so they can't give a good average for a county that has 15,000 people. This won't, prescribing wouldn't have happened as often, so your error is going to be really, so your confidence interval will be really wide, and they have a cutoff. If it's a certain, it's to a certain level or length, then they won't actually report it. It's also for privacy, because somebody could go into the data and say, oh, I have an idea who that person is, if it's a really small group of people. So that is due to HIPAA. So in this case, because we have missing values, we need to remove them. So, well, it makes it easier. That's all that's doing. So the population mean will be the mean of the entire group. Because we're missing values, this is a sample, but using everything will be as close as we can get to a population mean. And I want to just show that as an example. So we're saying our entire pretended say population is our mean overdose rate, and we're moving on to overdoses, is 6.8 per 100,000 people. So remember, the set seed is just so you'll get the same answers as me, because this is a lot of what I'm doing in random. So what I'm going to do here is I'm going to pick 450 random counties from my data set. So this is a totally random sample that I'm pulling out. So this is when we would use the confidence interval if we have a lot less values than is in our entire population. So we're pulling those random values out. So in order to calculate a confidence interval, we need to know what the mean is, the standard deviation. So that sample mean, so those 450 randomly chosen counties, the mean for those is 6.8. So that's actually, that usually doesn't happen. That the sample will look like the population. So then we're going to look and find our how many values we have in our data set. We check, there's 450, so the code worked. Now there's 450 randomly chosen counts in our data set. Now we're just going to find the standard error. So that's the standard deviation over the square root. We'll need that for our confidence interval. So we're seeing 0.25 in our sample. Now, here's the meat of it. So those were just, and a lot of this could be embedded in one another. I try to, the way I would normally code is to put the function for the mean in here and the function for the standard deviation in here and do it all in one line of code. I'm trying not to do that so that you guys can understand this intermediate steps. I accidentally did that last week because I didn't even think about it. So I'm trying to do that for you guys. So we have our, to get our confidence interval lower value, so the low value on our error bands, you can think of it. We would take the mean of our sample, and because in most cases you do not have the population mean when you're using it, it's not something you have access to. And then you would subtract 1.96, so we're doing a 95% confidence interval in this case, times the standard error. So that is our lower value. So we're seeing our lower value is 6.3. So now we're going to calculate our upper value, which is exactly the same. We're just adding the 1.96 plus the standard deviation. Now we're seeing our upper error value to be 7.3. Now, just to bring it all together, let's go up here. This is as close as we're going to get to a population mean. You're now seeing that that almost population mean, it sits in between these two values. You would expect that to happen 95% of the time. So if you did this over and over and over again, samples that I say you did it 100 times, exactly what I just did, you would expect to see 95% of those random samples fit within this interval. Might be one or two off. The more you can sample, the closer it would look to that 95%. So that's what a confidence interval actually means. So bringing that all together. So if you resampled over and over and over again, and drew this confidence interval over and over again, 95% of those confidence intervals will have the mean population mean inside their confidence interval. So does that make sense? Okay, great. So I am going to have you guys try this, but I tried to code the parts that you would have no idea how to do. All I'm asking you to do is this part, finding the sample mean, which is pretty self-explanatory. There are no missing values of the prescribing rates, so you don't have to worry about the NA.RN part. It'll look exactly like this. And then you're finding this is the sample size, which you need for the standard deviation here. And then you're finding your standard error. And then you go down and find a 95% confidence interval. You can fool around with it just if you want to. But I already, so then we're doing prescribing rates. Actually, I am going to go over one more example, but I am going to have you do the southern states. So I'm looking at the entire country here. So I'm going to go over prescribing rates so you can see this one more time, and then I'm going to have you do it, but keep that in mind. So you won't have to code this part. We're finding that random sample of 450 values, and then we are going to find our mean of that 450 value sample. In this one, there are no missing values, so there are 612 in our entire population. And this will actually be the population. because we have all the counties. So this is a great example of what it actually looks like. It's not an estimation. We know what the prescribing rate, we find the mean of all the counties. That's actually the number that it would correspond to. So if we find that population mean, it's 80. So 80 pills per 100 people. That population mean. So we're going to sample, then we're going to find the mean of our 450 item sample. That is 79. So it looks pretty close to our population mean. We should see 450 here because we took a 450 items sample. And then we're doing our standard error, which is standard deviation from the square root of the sample size or the amount of rows in our data. So that is 0.09. So that refers to how much error is in our data. So now we're going to do the confidence interval here. So we're taking, again, the mean prescribing rate in our sample minus 1.96, which is the z-score for a 95% confidence interval, times the standard deviation, standard error of our prescribing rate. So this is the lower bound, is how you'll hear it referred to, the lower bound of our 95% confidence interval, or our lower value in our error range. It's 77.6. So now all we do here is change it to a plus sign. It's 81.85. So the next piece of code does the population mean. That population mean, as we would expect, 95% of the time is within those confidence. So that's what it is in practice. I think that this helps to see it and say, okay, so that actually makes sense. So I subsetted the southern data to just the south region. I'm looking for NA values. So the way we would know this, so say I had, I'm looking at this table, so I'm seeing false for 192. So that means there's no missing data. So you don't have to worry about the NA.RN code. But now I'm going to find our population mean for you guys. So that's 7.66. I'm sampling 450. Or 150, sorry, because our sample size up here is 192, are for our full sample. So in both of these cases now, it will actually be a population mean. But I also sampled the overdose rates in the South and prescribing rates in the South, because that part you shouldn't know how to do. But I think hopefully if you understand the concepts, just follow the structure. The structure will look exactly the same. You'll just be doing it yourself. So go ahead and try to do that in the code. And I'll be here if you have any questions, I can float around.
Okay, so since you have the whole data set there, you probably, the whole purpose of the subsetting is just to show this, you would use the whole data set.
Well, that's what the sampling is for. The sample, we would never use a sample if we had the entire population, never. But I'm trying to show you guys that when you do sample a large enough value from a population, that the mean is most of the time going to be in that confidence. In practice, you would never do this. This is conceptual, so you can understand what a confidence interval is, what it means, and because we, in most cases, never have the population mean, so we have to do this for everything that we run.
So going back to the last one, where you had 20 missing values, does that count as not having a population?
Yes, that's why I said it's as close to a population mean as we can get, so it's not ideal. But it's probably going to be somewhat in the ballpark. If we have missing values, it is no longer a population mean. But
you would still use that data, though.
Yes. So I'm using that as an example. It's as good as we can get, basically, with this. The data doesn't have it, but we're pretending for now that it is the population mean, just so you can see that it's going to be inside that interval. The one really I would like to mention about missing values. So all those missing data are going to be small counties. So that's going to bias our data. So because they are small counties, they're going to look different than, say, St. Louis, Austin, those larger counties. So we're undersampling or sampling less small counties. So when you look at these results, you have to keep that in mind and know that you're missing some small counties, all of those values that are missing are going to be small. So when you look at your result, you have to keep that in mind.
So now I'm going to show you how to finish those exercises that I assigned. So just to recap, we subsetted the opioid data frame, which has prescribing and overdose rates to the southern region. When we looked at NA values, we found that there were none. For the overdose rates, in particular for the southern states, again, to recap, the population mean is 7.66, and the population mean for prescribing rates is 98.99. So we are going to set the seed again so that you get the same answers I do. So I set the seed. And here you can see I'm pulling from the overdose rate variable. I'm pulling 150 values out of the 192 that exists, and I am not replacing values. So we're not, once we pull a value, we are not putting it back in the pool. So I'll run that. So now we are then going to calculate our confidence intervals. So here, in order to calculate our confidence intervals, we have to first find the mean. So we're going to find the mean of this sample of 150 observations. We're going to see that that is 7.48. Next, we need our sample size. Since this is just a string of values or a vector of values, we can use the length function here to do that. So if we print it, the number of values is 150. That checks our work here to make sure it was done correctly. Next, we're going to take our standard error, or calculate our standard error. So this will be the standard deviation of the sample over the square root of the sample size. And in this case, when we run that and print it, we're seeing our standard error is 0.49 for the overdose rate standard error. So that gives us everything we need to calculate our confidence interval. So we have our lower bound .od.south. We're setting that as the variable name. So we take our mean and then we subtract 1.96, which is the z-score for a 95% confidence interval, times the standard error. So that gives us our lower bound here, which if we print it is 6.527. Now, if we want to find the upper bound confidence interval, we again take that mean and then plus 1.96, our z-score for a 95% confidence interval, times the standard error. And if we print that, our value is 8.43. So if we scroll up here, or I can just reprint it here. So we are looking at overdose rates right now. So we can see that 7.66 is within our lower bound and our upper bound of the confidence interval. So just to reiterate that if we ran that over and over again, without our seed set, we would say we ran it 100 times. About 95% of those times, our population mean would lie within this confidence interval. But 5% of the time, there would be random error where it did not. Most of the time, we don't have our population mean, but in this case, we do, so we can then demonstrate what is going on with this confidence interval. So the last exercise that I had you do was to do the same thing with prescribing rates. So I am setting the seed to 47 again. So I'm running my prescribing rates here. Again, we sampled 150 values out of our total sample. First, we're going to find the mean. The mean of the prescribing rates is for our sample is 99.05. Next, we're going to make sure and set to a variable our sample size. So just to check, yes, it took 150 values in that case. So the next thing we need to do is calculate our standard error. So this will be the standard deviation of our sample over the square root of the sample size. So if we run that, we're seeing our standard error for the prescribing rates is 1.928. So now here again, we're taking our mean value minus 1.96 because we're finding a 95% confidence interval times that standard error to find our lower bound of our confidence interval. In this case, the value is 95.27. So next we're going to take our mean, add 1.96 times our standard error, which will give us a value of 102.83. So if we go up and then print our mean prescribing rates, we're seeing that it's 98.99. So again, as we would expect, 95 times out of 100, this 98 population mean lies between our lower and our upper bound confidence interval.